All right, folks, we're going to continue our Hyperwall presentations this afternoon, but I want to appreciate Nikki giving us the overview of the NASA calendar. If you didn't get one, they're being distributed at the front of the exhibit hall here. Next up, it's my privilege to introduce Dr. Karen St. Germain, who is our Division Director for NASA Earth Science.
Thank you, thank you, thank you. It is so great to be here. I missed AGU last year. Because of the SWAT launch. It was, if you're going to miss AGU, that's a good reason. But it's so great to be here. All right, I am going to tell you a little bit of a story, and I'm going to weave in some of what we've been up to and what's coming up. Let's see, where's the best place for me to stand? I don't know if all of you have seen this animation yet. This is the GISS temperature spiral. And I'm just going to let it play out because it's a pretty impactful thing to watch. What you're seeing is annual temperature according to the months, starting pre-industrial age and then culminating in 2023. And by the way, you'll notice that 2023, that spiral extends pretty far out, meaning 2023 was a record-breaking year. This increase in temperature is, of course, driven by greenhouse gases. This is one of the culprits here. This is methane, one of the two most powerful greenhouse gases. Methane, of course, as many of you know, comes about from fossil fuel extraction, also. I'm not loud enough? Is that what you're telling me? Is that better? Okay. Thanks to my support crew over there. So methane, as many of you know, is comes into our atmosphere through various methods or various situations. One of them is fossil fuel extraction. Agriculture is another producer of methane, as is any sort of decomposition. All of those things contribute methane into the atmosphere, and methane is a very powerful greenhouse gas. So NASA Earth Science, what do? We try to understand how the Earth operates as a system and how that system is changing, but we're going further than that. We're trying to put information into the hands of people who are trying to mitigate future climate change and or adapt to the change that is here and is coming. Sort of a cousin of greenhouse gases is air pollutants. Very often air pollution comes from the same sources as greenhouse gases, and you can sort of think of them as forerunners. Their health effects are immediate, whereas greenhouse gases take longer to affect our health. But one of the things that NASA does is identifies a problem, develops the technology, and then launches a system to go after that problem. In this case, we were really looking at air quality, and our team from Langley and the Smithsonian Astronautics, did I get that right? Astronautics Institute, built the TEMPO instrument. It was announced by Time magazine as one of the year's best inventions. And this is the TEMPO launch. Now, one of the things that TEMPO measures is nitrogen dioxide. Nitrogen dioxide is kind of a brownish gas. It is a byproduct of combustion, and it is it comes about because from industrial plants as well as transportation. So it's a problem in a lot of our urban areas where we see a lot of those kinds of sources. But it's not just nitrogen dioxide. When sunlight hits nitrogen dioxide, it changes. Chemically it changes, and it produces ozone down at the surface where it is an irritant for human respiration, right? So, ozone up high, good. Ozone down low, not good. So TEMPO is going to measure nitrogen dioxide. Now I'm going to start you off with, this is how nitrogen dioxide has looked to us for years from the OMI instrument. And you're seeing over time, this is actually a pretty good news story. Nitrogen dioxide over the United States has actually decreased over time. From 2005, where you saw, particularly in the urban centers, very high levels, decreased over time. But with OMI, we only had, we didn't get to look very often, and we didn't get to look at fine spatial scales. So we could tell the urban centers were seeing elevated levels, but that's about it. Now, let's try this again with tempo. Now you're looking at tempo data. Tempo is in geostationary orbit. It gets hourly look at nitrogen dioxide and other pollutants. Where you see the black areas, that's cloud that the instrument can't see through. But this is not just hourly looks, it's at the neighborhood scale. And we are already seeing results from tempo that correlate higher pollution levels with the demographics of the neighborhoods that are most impacted by those. And it probably won't surprise you to know that many of those neighborhoods are from historically underserved communities. So this is giving us the data that can inform future zoning, regulations, where we put schools, all of those kinds of decisions that happen at the community level can be informed now by tempo data, and we hope will lead to better health outcomes and better educational outcomes for the students who are living in these areas. So that's one of our recent missions, but I mentioned when I opened that we're trying to, again, discover, understand, and then have an impact on society. And that's a new strategy that we're developing. And I'm going to give you one quick example. This is an example from Bangladesh, and I don't know if, nope, sorry. Not an animation. Really having trouble with the slides here. Hang on. Sorry, folks. Okay, Bangladesh. So Bangladesh is a highly agricultural society. One of the biggest crops there is rice, and rice is a high consumer of water, and this is a real challenge for Bangladesh in managing their water resources, particularly during the dry months, because rice is so water intensive. They'd have to pump water from their aquifers to farm it. So we recently teamed up with the government authorities in Bangladesh using Landsat and Sentinel-2 data, GPM data, and global forecasting data from GSF to come up with a methodology that informs how much water they actually have to pump. This saves not just the water, it's saving 30% in agriculture water waste. It's also saving 45% in energy consumption that is required to pump that water, and over $100 million in subsidies that would have paid for the pumping of that water. So it's a ripple effect when we can help agriculture, when we can help farmers, producers be more efficient with their resources. We're doing this in the US, this is a Bangladesh example, but we're doing this around the world. Okay, another thing we just opened up, so that's on the mitigating the impacts of climate change. This is on the mitigation of future climate change. We've opened the Greenhouse Gas Data Center. This just rolled out. You can get to it. I don't think I see it on the slide here, but you can get to it by going to earth.gov/GHG Center. This is a multi-agency. You see the initial founding partners up at the top. One of the things this portal is doing is bringing together a wide variety of greenhouse gas data from satellites, but also from surface, trying to put together a comprehensive understanding, at least over the US, for starters, of where the greenhouse gases are coming from and how they are lingering and distributing themselves in our atmosphere. We're also building in the natural sources and sinks of greenhouse gases into this portal as well. So this is a new capability. It's going to be evolving over time, but just rolled out, and it's pretty exciting stuff. All right, what's coming up? Nikki mentioned it. We have the PACE launch coming up. This is at the end of January, early February. We're still negotiating the launch pad situation. But PACE is going to do for the biology, our understanding of the biology of the oceans, what SWOT has done for our understanding of physical oceanography. In other words, it's going to give us an unprecedented view of the phytoplankton that grow in the upper layers of the ocean and play a critical role, a critical but not yet really well understood role in the carbon cycle. When we think of taking up carbon from the atmosphere, a lot of us think of trees, right? Go out and plant some trees. Well, turns out the phytoplankton play as big a role as vegetation on land in moderating carbon in the atmosphere. So PACE is going to give us an unprecedented understanding of phytoplankton, also algal blooms, harmful and not, as well as the interaction between the oceans, what grows in the upper layer of the oceans, the aerosols, and the clouds. So really looking at process studies as well. So look forward to that launch coming up in about a month and a half. And then following on its heels will be the NISAR launch. NISAR, as many of you know, is our biggest, not just NASA's biggest, but I think the biggest U.S. collaborative project with India. We're building this mission with ISRO, and it's a synthetic aperture radar mission, L-band and S-band, the first time that's ever been done. It will give us an unprecedented understanding of, frankly, anything that changes position on Earth, whether we're talking about glaciers, volcanoes, earthquakes, a long list, deforestation. Any of those things we'll be able to see with NISAR at unprecedented fidelity. So I'm going to just sort of come back to where I started. The NASA Earth Science Fleet is now over 24 strong, with new missions launching that are giving us an ever increasing understanding of how the Earth works as a system, how it's changing, how we can adapt to that change, how we can mitigate future change, and continue to thrive on this beautiful, beautiful planet that holds everyone we know and love. Thanks very much.